share my screen again. Oh, this is not the reason why this broke down. Okay, it didn't save everything, but I got most of it. Okay, what I wanted to start with, and because this broke down, I'm not gonna try to do too much because I don't want to waste time. But I wanted to, and I'll try my best to just release this to you guys in a PowerPoint. You can look over this later. Is to get a feel for nucleophiles, right? So I think just one thing that's maybe coming up is convenient to recognize the nucleophile in these reactions, just because they typically are the main reactant over the reaction arrow. It's good to have some type of naming system. Obviously, does it make your life a little bit easier. Once we move into eliminations, there's a thin line between a base and a nucleophile. So we want to be comfortable with things that are starting to be presented. So whenever I have a triple bond and there's a metal to it, in this case here, there's a lithium or a triple bond in with a sodium. These classes of compounds are typically referred to as acetylides. So the name of this system would be lithium acetylide or here sodium acetylide. And acetylides are very, very good nucleophiles. If you look here again, this carbon there's a carbon metal. So carbon is a non-metal and there's a metal bond. So that means this bond is ionic. So truly the way you should think about this is that carbon has a negative charge and the metal has a plus charge. There's an electrostatic interaction here. So these are great carbon nucleophiles. All right, these are going to make carbon-carbon bonds. All right, we have also on the other side the oxides. This is where you have an RO minus charge. So in the case here, if I have sodium OMe, this is sodium F oxide. If I have lithium instead and I have an OET, this is lithium F oxide, right? So the alkyl group is based off your carbon chain. Here's an ethyl, so it's called an F oxide. Here the alkyl group is an ethyl, so it's an F oxide group. Okay, we have amides. I know this is spelled like a mides. My organic professor was like from the West Coast, so he said that typically when you have the functional group where there's a carbon oxygen double bond nitrogen, that's known as a amide. But when you have the inorganic salt version, this is known as an amide. All right, but I've seen people use that interchangeably. It's okay. I just want to make sure you know which system you're dealing with. But if there's a negative charge on your nitrogen, that's also a great nucleophile. And typically, we refer to these as amides or amides. So in this case here, LiNH2 is lithium amide or lithium amide. Okay, and then we have the organic metallics family. Right, the first family is the organolithiums. Right, so you can have a regular alkyl chain with a lithium. You would just call this butyl lithium here because there's 4 carbons in the chain. Depending on the alkyl chain, you would use that. You could have set butyl lithium. You could have tert butyl lithium. Right, over here, if I have this lithium attached to a carbon directly involved in a double bond, in this case here, this is a vinyl group. So this is known as a vinyl lithium. Over here, I have this big aromatic or benzene ring. We know this is a phenyl ring now. So this is referred to as phenyl lithium. On the opposite end of organic metallics are the Grignards. Grignards are unique because they're going to have an R group in the alkyl carbon with magnesium X. And X again stands for any halogen. So here I have 2 carbons in the chain. This is ethyl magnesium bromide. Here I got a double bond again. This is vinyl magnesium chloride. And here I have my phenyl ring again with an iodine. So this is phenyl magnesium iodine. All right, so these are all potential nucleophiles, and these are in the strong group. I know these are strong nucleophile because there's a negative charge, right? Whenever I see a metal present, I know that metal is going to have a positive charge, and the anion directly attached will have a negative charge. Okay. Down here, I had some other stuff that I was trying to work on. Is our typical alcohols, thiols, amines, right? These are compounds that have lone pairs that will also participate in being nucleophiles. These are pretty neutral, all right? Also, you can have the carboxylate or the amides. because they have that carbonyl next nearby the oxygen, they're going to be able to participate in resonance, and they won't be as strong as the alkoxides, right? So it's OR, right? So I'm going to try my best to finish this and send this to you guys, but having a clue about potential nucleophiles will make your life a little bit easier, all right? So let's start working on the assignment here. Where is it? It's not here. And let's kind of go through these case by case if we can. All right, so mentally, conveniently at this point, I've already established that these are all substitution reactions. So I know that this can either be an SN1 or an SN2. So I just need to kind of make sense of what's here and try to guess which mechanism type. And then from that information, I should be able to predict the major product. All right. So before we start to work on problems, let's kind of review really quickly. SN2, all right, there's no rearrangements here. So the only thing I need to concern myself is with stereochemistry, all right? If my leaving group is on a wedge, my nucleophile is going to be on a dash. Or if my leaving group is on the wedge, if my leaving group is on a dash, then my nucleophile should be on a wedge, all right? You guys are comfortable with every SN2 reaction having inverted stereochemistry, all right? So keep that in the back of your mind. Okay, the second thing here is I need to know which conditions favor SN2. Strong nucleophiles, polar aprotic solvents, and any primary, secondary, or methyl alkyl halides are okay. No tertiary alkyl halides can do SN2. Keep that in mind. Okay? On the opposite end is the SN1 reaction, right? And what's very important to think about with SN1 is the fact that carbon cations will rearrange. So whenever I select an SN1 mechanism, I have to mentally think about possible rearrangements. There's 4 ways that a carbon cation can rearrange. First is with a hydride, right? That's the first thing you're looking for. Are there neighboring hydrides to the carbon cation? Second is the methyl shift. If there's no hydrides, is there a favorable methyl that can move, right? The third way is a ring. So if I generate a carbon cation and if I have a ring nearby that's strained, then I can do a ring expansion. And the last way a carbon cation can rearrange is through resonance. So typically there needs to be a double or triple bond near that carbon cation. If I can resonance delocalize, that's also to potentially stabilize the carbon cation. So keep that in the back of your mind. SN1 has the ability to undergo carbon cation rearrangements, right? So how do I know if a mechanism is going to go through an SN1 type of, or how do I know the conditions are favoring an SN1 mechanism, right? So I can look at my alkyl halide. Tertiary, secondary alkyl halides prefer SN1. No primary unless there's a potential rearrangement, okay? The second thing is my solvent. I need a polar protic solvent, right? I need an H somewhere, an acidic H in my solvent that can participate in hydrogen bonding, okay? And my nucleophile strength does not have to be strong. Weak nucleophiles can work in SN1 fashions, right? So considering all those things, we should be able to make some sense of the potential products. All right, I need to add a methyl group here, so I want to just, yeah, this is fine. Just put a methyl group there. So sorry, I just needed that for the stereochemistry here. Okay, let's do this first problem. You guys are going to help me out today. Can anyone tell me what type of alkyl halide do I have here? Can you guys see this first molecule with the bromine here?
Yes, secondary.
Okay.
Very.
Good. This is a secondary alkyl halide. What type of nucleophile do I have? Is it strong or weak?
It's neutral.
Okay, think about it one more time.
Okay, how do you define if it's strong or neutral?
Okay, I look at it if it's ionic. And I guess the trick, the trick that can help you guys. Anytime there's a metal, it's going to be ionic. So I see a big sodium there, right? So now that sodium and carbon is going to have an ionic bond. So that means that carbon is going to have a full what charge?
Negative.
Yeah,
Negative
negative charge.
charge.
Yeah, negative charge. Good. So if that has a negative charge, what is going to be? Anybody?
Strong.
Yeah, that's going to be strong nuclear.
Yeah, it's gonna be strong.
Okay. What type of solvent do I have here?
I have here.
Polar aprotic.
Okay, good. That's a polar A product. So my conditions are going to favor what type of mechanism?
SN2.
That's right. Can you describe the nature of the product?
You're gonna have the inverted product.
Okay. So if you can, at your desk or at your house, go ahead and try to draw that product for yourself. I'll give you a few seconds.
Dr. Cooper, I have a question.
Go ahead. Yes,
So for SN2, chiral and achiral don't matter. It's always going to be inverted.
Oh, it does matter if it's chiral or achiral. Sometimes you could do SN2 at a carbon that's achiral. So that means that when you draw the product, there's no stereo.
Okay. So chiral does matter for both.
Yep. Chiral matters for all systems, SN1, SN2. So the only thing is just be conscious enough to recognize if the carbon, if the nucleophile attacks a carbon that's chiral, you have to show stereochemistry. If the nucleophile attacks a carbon or if it rearranged and is achiral, then you don't have to show any stereochemistry. Does that help a little bit? Yes, no?
Yes, it's just that when you threw the methyl, it threw me off.
Yeah, I put the methyl here to make this carbon chiral. I already was indicating a chiral center with that wedge. Without the methyl group here, it's not chiral. It's achiral. So it wouldn't have made any sense to draw a dash here.
Okay, two questions.
Yes, ma'am.
So, you don't put the metal when you redraw it. You don't put the metal.
No metal, because the metal is going to be with the leaving group. So you're going to form as a byproduct sodium bromide.
So we add that at the bottom.
I don't need to see it. I'm interested in the organic part. But if that helps mentally to keep track of things, you can.
Okay, and my next question is, okay, say it was a double bond to that carbon. Do you count would it still be secondary, or do you count all three lines?
So if it was a double bond here,
Right.
Yeah, that's a good question. I mean, technically, it still is secondary, but we changed the name completely, and that's why we. I guess that's kind of why we changed the name. We want you guys to recognize that there's a double bond here. This is actually called a vinyl bromide. And
Okay. And can you explain how that will be vinyl?
Yeah, whenever you're attached to a double bond, directly attached to a double bond, we always call that vinyl.
Okay.
And that changes the chemistry. We just want you guys to recognize that there's a double bond here, it cannot do substitution chemistry. You can have a vinyl nucleophile, but you can't have a vinyl as your leaving group type of participant, or I guess you'd say your electrophilic site. A nucleophile cannot attack a carbon that's involved in a double bond. There's some other chemistry that happens. Typically, you need a metal type of reaction. We'll talk about those in the next chapter.
Dr. Cooper.
Yes, ma'am.
Do you want us to
label like this strong.
No. Well, I'm probably going to ask some questions like this on the test. There's a section where I do this first, and then I might just ask you guys to later on just give me the products. But yeah, this is my teaching strategy to be able to know which mechanism type you got to think about these things. What type of alkyl halide, what type of nucleophile, what type of solvent. All these things are important to kind of determine what mechanism is favored for the product formation.
Dr. Cooper, I have a question right quick on the mechanism.
Okay.
So for the SN2, the nucleophile has to be strong to force to attack the carbon, which pushes the halide off.
Yes.
Okay.
Yes. It's all concerted. I can probably generate a mechanism here. Yes. If you want to think about it, I'm going to put the charges here. There's a plus here on the sodium. There's a minus here. Yeah, it's not liking that where I place that charge at. Okay. You know what? I'm going to draw my own arrows. I think it's going to be where I want it. All right, the nucleophile is going to attack that carbon. All right, and then the leaving group is going to leave. Come on here. Okay, so nucleophile attacks, leaving group leaves, and this sodium is going to be attracted to that Br. And then now you're going to have this coming in from the back.
And why is the nucleophile not considered neutral?
Because there's a metal non-metal bond there. The bond nature is ionic. To be neutral, you kind of need to be covalent. You need to have all electrons shared. But ionic compounds don't share electrons. They're completely transferred. So the carbon has all the electrons.
So if this was on a test, we would have to draw the arrows just to product.
Yeah, it depends on the nature of the question. If I ask for the mechanism, show me the mechanism. But if I ask just for the product, you can just show me the product. I will ask for some mechanisms, but I don't need to see all mechanisms. That helps. And did I answer the question about being neutral? You only can be neutral if you're sharing electrons. Okay, no questions? Can we try this one down here? Well, you know what? Let's stay on the first row. Let's do this one right here. Okay, the one on the right. What type of alkyl halide is this?
Secondary.
Right?
Yeah, this is also secondary alkyl halide. Good. Type of nucleophile that we have here. Is it weak or strong?
Strong.
Yeah, that's strong. Good. And easily, if I see a metal, it's going to be strong, right? This is going to have a negative charge. This is going to have a positive charge. And what type of solvent do I have? DMF. What type of solvent is that?
Polar aprotic again.
Yeah, that's polar aprotic. So my conditions are favoring which mechanism type here?
SN2.
It's also SN2. Okay. So what's the product in this reaction?
The product is going to be a wedged Cl. Oh, well, not a wedged propyl group with double bond.
Okay. Yeah. Good. So the trick here is that the nucleophile has to retain all of its features. All right, so if we look at this nucleophile here, the lithium and that methyl are trans to each other. So make sure you guys draw those two things trans. That's one of the things I wanted you guys to look at here. Let's see if I can. Barely flipped it. Just remember that these two groups have to be trans. But good. Any questions with this one?
I have a question. I'm just confused about how you drew the double bond like that on the group that you added to the wedge.
Okay. Let's see. Maybe this helps if I put some letters here. Can I put A, B, C here? So A is my nucleophilic site. All right, so once I go back, this is A, and it's going to be double bonded to B. And it's going to be a methyl group that's C, right? So all I did was react at this carbon. I replaced the Cl with this carbon A. So carbon A is attached to that carbon there. And I just wanted to make sure that I placed my C where it was still trans across this double bond.
Oh, okay. So you're just basically attaching it where the nucleophile was.
Attached to what you mean where the leaving group was?
Or yeah, you're attaching the nucleophile where the leaving group was. Yeah.
Yeah, that's right. That's right.
Okay. Thank you.
And what two things are trans?
It's the bond to the the bond to the electrophilic carbon and C. So in this case here, you see like lithium and methyl are trans. So that same relationship has to be expressed in the product. So where now all the carbons of the original alkyl halide are trans to that methyl of the double bond here. So I guess the thing that if you want to look at, if you put the methyl group here, it would have been wrong. Right? So it does matter where that methyl group is at. This is a cis relationship across the double bond, right? So if you put the methyl here with that, these two things are cis across the double bond. But putting the methyl group here reserves the fact that it was trans in the starting material.
Okay.
Does that help out?
Yes.
All right, I'll do the mechanism again. So the mechanism starts at the bond here. And the reason why is because that bond carries the electron density. Let's make that red. Oh boy. Let's add a full arrow at the end. All right, and then I'm going to break the bond to the leaving group here. It's a little too close. Perfect. Okay, so that's the reaction here. If you want to look at the byproduct is just lithium chloride. But again, you don't have to show this, but if this helps keep track of things, you can. It's just a salt disobedient solution. Okay, any questions so far on those first two products? Okay, good. Let's move down to the next one. What's going on with what type of alkyl halide do I have here?
Primary.
Yeah, this is primary. Okay. What type of nucleophile do I have?
Weak.
Strong.
All right, I got two things here. Anybody else want to chime in? What type of nucleophile? The correct answer is weak. This is weak. How do I know it's weak?
It's no metal.
Yeah, there's no metal. So it's lone pairs on the oxygen. So this is a weak nucleophile. So also this is participating as the nucleophile and solvent. We call this the class of reaction. What type of reaction?
SN1.
Or yeah, it's going to be SN1 mechanism, but the class of reaction is called subolysis. When your solvent becomes your nucleophile and the solvent. What type of solvent is this? Polar what?
A product.
Not a product, but this is polar
Product.
product. Yeah. Okay. Good. And it's product because of the H on the methanol. So this mechanism type, you guys told me already, is SN what?
One.
SN1.
Okay. So SN1, what's the number one thing that should come to your mind every time you think of SN1 reactions?
Two-step.
Racemic mixture.
Two steps, racemic mixture. Okay. That's not the first thing to come to my mind, but those are good things. There's something else I'm looking for.
Hydride ships and stuff like that.
Yeah, rearrangements, carbon cation rearrangements, right? They got to be natural to you guys. So you need to, hopefully you can mentally see that this is going to rearrange. But if not, it's okay. Let's look at this. The first step is my leaving group leaving to form. I didn't want to draw the limbs and the lines. Okay. This thing here. So typically we say that primary alkyl halides don't even react in SN1s because the corresponding carbon cation is no good, right? This primary carbon cation is very, very unstable. Right? There's no carbons to really help stabilize it. But there's something that can happen. What can happen?
You can do a hydride shift.
Yep, that's right. So there can be a potential hydride shift here.
Dr. Cooper, can you only do these shifts on SN1s, not SN2s?
It has to be carbon cations, but yes, carbon cations only form for SN1. That's correct. Good.
Why can't you do a methyl shift?
Okay, you could do a methyl shift if you wanted to, and all it would do would just you move a methyl up here. So you go from something that's primary to what down here. So if you move a methyl, it would be secondary. All right. If I move a hydride, I go from primary to what?
Tertiary.
Tertiary, right? So that's why the hydride shift is better here than the methyl shift. But it's good that you saw that. All right, I'm not going to do the methyl shift, but you're more than welcome to try that at your leisure. All right. Sorry, I need control over the ball limbs quick. All right, so what's going to happen here? I'll just make my own arrows. I don't trust this anymore. All right, I'm going to have my hydrogen is going to do a hydride shift here. All right, and so I'm going to have something that's initially it was primary, but it moved to something that was tertiary. All right, I'm just keeping track. Actually, I'm not going to do that. You guys can count my ankle at this point. You guys know what's going on. All right, so this one's from a primary to a tertiary carbon cation. What's the last step here now?
You have to finish attaching your OH group.
Okay, good. So the nucleophile is going to come in, and my product now is going to be do I need to draw both the wedge and the dash products here?
No.
Okay, good. And the reason why I don't is because this carbon here is achiral, right? So SN wins because there's a nucleophile present. You do attack from the top and the bottom, but in this case here, you don't have to show the stereochemistry because the center is not really chiral at
I have a question.
I have a
Why
question.
OME?
all. All right, because this is a weak nucleophile, you have to lose the H in the mechanism.
Okay, so when it's weak, you just take the H off.
That's correct. It's going to be charged if you keep the H on there, and your final product cannot have a charge. Okay, next question. Did that answer your question? Okay, there was another question. Go ahead. I'm sorry.
So on Friday, you said something about there's a difference between drawing the single-headed arrow and the double-headed arrow.
Yes, that's right. In these processes for substitution reactions, they're all double-headed. Single electrons, you need a single-headed process. There's only one way to do single electron chemistry. You have to form a radical.
Okay.
But when you're dealing with bonds, there's always two electrons in these bonds. So the hydride is moving with the H and two electrons. Nucleophiles are attacking with two electrons. These are two electrons attacking. Leaving group is leaving with two electrons. Or the same as saying a lone pair, right? A full lone pair is moving or attacking. Okay, good questions. Any other questions?
Yes. Okay. Can you go back and explain the hydride shift? Like, why did you? Well, I know you said that it's H's on all of these carbons, but why did you specifically move that one?
Okay, yeah, good question. All right, you only look at the carbon that is neighboring the carbon cation. All right, so don't go this over here and over there. That's too far away. Hydrogens can't shift through a carbon over here. So it can only happen at the neighbor. So the neighbor has an H or a methyl that could potentially shift, right? And if we move the methyl over here, the plus just moves here, but this methyl is gone, right? So this becomes secondary. If we move the hydride, we go from primary to tertiary. So the rearrangement is always going to occur where it gets to be the most stable carbon cation. So the tertiary is more stable than the methyl. Or I'm sorry, tertiary is more stable than the secondary carbon cation that came from a methyl shift. But maybe I can say this helps a little bit. Rearrangements also is going to occur by kinetics. And kinetics means like what happens the fastest. It's easier to move in hydride than it is a methyl. So the methyl shifts are kind of like, if there's nothing else possible, I will move a methyl, but hydride shifts occur very, very rapidly. So you should probably train yourself to think about hydrides first. If a hydride shift can occur, I would try to move it. If there's a better carbon cation that comes through a methyl shift or it's a type of ring expansion, then you would do those next. Does that help?
Yes. And then, okay, when you add on your final product, where you add the line, so this when you add the line where the positive charge is, it just turns out to be this because of the geometry, right?
Yes, I think I understand what you're saying. Not really fully, but you mean the way it looks this way? This is the only way to. I mean, that's not the only way to draw it, but this is a convenient way of drawing it. Just because my carbon kind of looks this way, I just added an extra bond to the methoxy group.
Okay.
But yeah, you could have moved things around. I mean, could have did something like this if you like it. I don't know. Right? That's still the same thing to me. It's like it's really a tert-butyl group, right? So however you feel comfortable drawing it, it's fine.
Okay.
Okay, good. Any other questions? Good questions. Good questions.
Will we add the HCl to this one?
You can if you want to, but you don't necessarily need to. We'll put it here if you like that.
So you don't require those in your test. As long as we have the drawing, that's fine.
Yeah, I just want the organic part. I'm not interested in inorganic material. That's right. It's all organic. If there's a carbon and you didn't draw the carbon stuff, you lose point. But if there's no carbon, I don't need to see it. HCl has no carbon. Sodium bromide, sodium lithium has no carbon, so you're okay. Just all carbons I need to see. Was that a question? I think I answered very low.
Oh, okay. I was just going to ask, like, when are you going to? When is the time you want to write the test?
Oh man, it's so low. I can barely hear you. One more. Can you say it a little bit louder?
I said, can you hear me now?
Yep. Keep screaming. Keep screaming.
Okay. So I was asking if like when you were going to open up the notebook for us to pick the times to take the test tomorrow.
Oh no. I moved the test back. It's not tomorrow. But I can set the notebook up tonight. But it's not going to be tomorrow. I need to do eliminations. Yeah, I was thinking about that this weekend. It's going to be. I think it's going to be too much to try to put eliminations with the ladder material. So I'm gonna keep pushing to get eliminations in, and then I'm coming up with a strategy to get the last 2 chapters in. You know, things didn't work out the way I thought they would when I made the planner. But it's not your test. Your test is definitely not tomorrow.
Okay.
I need at least one more lecture to get into elimination. Actually, I need almost 2 lectures now. I'm thinking about it.
All right. One more question.
Yes, ma'am.
For like this one that has the SN1 reaction, the chlorine one that's polar protic.
Yes. Go ahead.
Okay, so it does not have a solvent on that. Does that automatically make it an SN1 reaction?
Yeah.
Huh?
Yeah, it does. It does. I mean, you guys are trying to force me to say things I don't want to say, but yes. Typically, all Savalas's reactions are SN1. And the reason why I don't like to give definitive answers, because it's always a way to generate a reaction that could be different than what you think. And there's some tricks that I use because you want to also just not see one thing over the arrow and say automatically Savalas's and go into SN1. Now, if I give you a primary alkyl halide that could not rearrange, then this Savalas's reaction won't work. Right. So that's why I'm trying not to say too much, because you do have to consider all components. A primary alkyl halide or a primary carbon cation will not form. This primary carbon cation did form because there was a potential rearrangement set up for it, right? But if there was no rearrangement set up here, this would be a failed reaction. No Savalas's could happen with a normal primary alkyl halide. But typically, all reactions with just a solvent are going to be SN1 type. That's right.
Okay.
Did that answer?
Yes, it did.
Okay. Good. Could we come over to this one? What type of alkyl halide is this?
Secondary.
Yeah, secondary. What type of nucleophile? Wicotron.
Strong.
Yeah, strong. What type of solvent here?
Polar protic.
This is a strong nucleophile and a polar protic solvent. So what is my reaction mechanism?
SN2.
One more time.
Oh, wait.
Think about
Well,
it.
I'm confused because SN1 needs weak nucleophiles.
Yeah, it's really so. That's good question. you guys are getting the hang of it now. It's a solvent dominates a lot of this, right? Strong nucleophiles can go for SN1 and SN2. Doesn't really matter. And if you think about it, sodium hydroxide and water, this just makes more hydroxide anion, right? So this is really just, it makes the same nucleophile in solution. But the solvent is protic. So this is going to move the reaction conditions to SN1, right? So keep that in mind. Solvent is in large amounts. That's why we call it solvent. You probably take like a few milligrams of this and dissolve it in a few, like maybe 10 milliliters, 15 milliliters of solvent. There's a lot of solvent molecules there, right? And that solvent has no problem hydrogen bonding to that chlorine. And when it hydrogen bonds to the chlorine enough, it's going to become completely solvated. Water is set up to deal with ions. You guys know that, right? It's a polar solvent. So it would love to be a plus charge in solution and a negative charge. No different if there's sodium chloride here, right? That would dissolve in water, right? This carbon cation and chlorine minus is also going to dissolve in water. So this is going to facilitate this bond breaking. Okay, so we realize this is SN1, and the big thing to always keep in my mind is what potentially with SN1 reactions?
Rearrangements.
Yeah, rearrangements. That's right. So let's take a look at the carbon cation that forms. So I'm going to form this carbon cation here, right? And you guys would classify this as what type of carbon cation?
Secondary.
Yeah, this is a secondary carbon cation. All right, so what can happen? Could this rearrange?
No, because that has 4 bonds.
No rearrange because of 4 bonds. I don't think I'll follow that one.
Like you can't hydride shift it, because if you move it over, it's gonna make a primary. If you move it to the left, it's not gonna be a classification.
Okay. That's a little tricky, but let's how I'm trying to respond. Maybe I want to say, just think about it a little bit deeper, right? So let's take a look at next door on the right hand side. Are there any hydrides here?
Yes.
There's 3, right? So if I move a hydride over here, my plus will generate here now, and that will go from secondary to primary. And is that productive?
No.
No.
So that's not a good shift, right? But let's go to the left-hand side. Is there any hydrides over here?
No.
No hydrides. But is there anything over here that could shift?
A methyl.
Yeah, methyl. So this is when a methyl shift now becomes productive.
You lost me.
Okay.
When you were at the one with the carbon with the 3 lines, why is there not a hydride? I thought it's 1 hydrogen. No, okay, it's 4 lines. Okay. Never mind. I got it.
Okay. So there's no hydrogen, but now there's a methyl that could shift. So let's go ahead and do a methyl shift here. All right, so somebody was close earlier. I'm sorry, I can't look at the names. I'm in ChemDraw right now. I pretty much got a clue who voice it probably was, but I don't want to put someone on the spot. But that was good. You saw that the hydride shift wasn't productive, but keep in mind that there was a methyl that could shift. So now I do the methyl shift, and I go for something that's secondary to something now that's going to be what?
Tertiary.
Yeah, it's going to be tertiary. That's right. Y'all really going to force me to make a test now. I'm going to probably give away all my potential reactions. It's all right. I know I can come up with something. Okay, so good. So now I have this carbon cation. What happens at this point? Nucleophile attacks, right? The carbon cation. So my product is going to be compound here, right? Do I need to draw the wedges and dashes?
Yeah, it would be racemic.
Okay, take a look at that carbon that has a nucleophile. Is it chiral? This carbon right
Oh no, we changed it. No.
here, it has 2 methyl groups. That's right. So it's not chiral, so you can draw a straight line there. That's fine. Okay. Any questions so far on that reaction?
Okay, so I get that the metal lithium isn't going to be there. Wait. Yeah. Okay, the lithium isn't going to be there, but I thought we got rid of the H. No, because we didn't do a hydride, right?
Yeah, we did a methyl shift.
So you only lose the H if it's a hydride.
Lose an H.
Like in the previous problem, how we just had O methyl.
Oh no, that's coming from the nature of the nucleophile, right? So the nucleophile is weak, so that H comes off of this one. This is a strong nucleophile, so this is Li plus OH minus. So OH is the nucleophile already.
Okay.
Does that help a little bit?
So on strong, the H stays in SN1.
That's correct. So the weak version of this would have been water, right? So that means if water was here, I would have to lose an H off of water, and I still would have got OH, not OH2.
Okay.
Good. Okay, good. All right, let's work on this next problem on the right here. Can barely see it all. Okay, good. So what type of alkyl halide is this one?
Primary.
It's a primary alkyl halide. All right, what type of solvent do I have?
Polar protic.
Yep, polar protic solvent. What type of nucleophile do I have?
It would be strong.
Right, strong. There's a metal there. Right. So that means that
Question.
oxygen has a negative charge. Yes, ma'am.
Why is ethyl hydroxide polar product?
There's that H there, acidic H in the solvent.
Yeah.
So that's why it's polar protic. The H is acidic. That makes it protic.
Okay.
Okay. Good. So what's my mechanism type here?
SN1.
SN1. Oh yeah. I'm sorry. Yeah. Thinking of something else. Yeah, this is SN1. I'm so sorry. This is SN1. Good. So what happens in my first step? I'm going to generate a what?
Carbon cation.
Good. I'm going to generate a carbon cation. That's right. And we want to make sure that the carbon cation doesn't do what?
Rearrange.
That's right. This is probably your first tricky one here. Looks like it's 2 potential products. Okay, so first of all, this could rearrange itself. Can you guys tell me how? Or
It could rearrange by resonance.
yeah, that's right. So only thing that's nearby is that pi bond there. Very good. I need for that to happen like that. Don't tell me I did that again. Boy, hope I didn't break my computer. Okay, I'm gonna keep it red. What did I do? All right, so resonance here, and this is just all, got the wrong arrow here. It's going to allow rearrangement from a primary carbon cation to a Was this productive?
No, because they changed that to primary. It was still primary.
There was nothing really productive about that move, right? But doing so, our two compounds are exactly what? Can you guys tell? They're identical, right?
There isn't.
They're resonance structures, but they're identical structures. Putting a plus at this carbon or that carbon is the same for this molecule. So it's good that you saw the potential resonance here, but that resonance didn't really have any utility, right? And this double bond down here cannot really participate in resonance here. And you need to have a plus at that central carbon for this to be involved. All right, so what is my final product then? Is this right here. Okay, so the question is then, why did I build a question that had a resonance that we didn't need? Did anybody guess why I did this?
To practice with resonance?
Yeah, that's a reason. But the main reason is this: a primary alkyl halide typically would not have done an SN1 reaction unless there's a rearrangement or resonance present, right? So the resonance here just allows this carbon cation to form, right? So this carbon cation is just not localized on one carbon, it's really delocalized on how many carbons? 2 carbons, right? So that means that this would leave to form a primary carbon cation that just has resonance delocalization to help stabilize it before the nucleophile comes in and generates a final product. Okay, good. Any questions?
Yes. Okay. So I completely understand why you didn't do resonance, but just by just looking at the problem, why wouldn't you consider hydrides or methyl shields? Because, like you said, all of them have H's, and with the methyl ship, it's one methyl on that carbon.
Okay, so the thing about methyl ships and hydride ships, they cannot be involved to any double bonds. The strength of a hydrogen or a methyl to a double bond is too high to shift. So they have to only be from single bonds. So if you look at this carbon, the carbon that has a carbon cation, only the neighboring carbon or the carbon is attached to can give it something to shift, right? So if we look at this carbon here, there's no hydrides on that carbon. So it can't do a hydride shift. And if you think about this carbon, it's involved in a double bond, or this carbon up top. So these are not really methyl groups. They're just kind of like these vinyl carbons, and they can't shift. So these carbons can't shift. So no hydrides, and the carbons that are attached to that central carbon here are not methyls. So there's no hydride or methyl shift possible.
Okay.
All right, good. Good questions. Good questions. All right. So the only reason why there was resonance here is to give you a productive reaction, right? If I did not have the double bond here, this would have been a no reaction, right? You cannot form a primary carbon cation and have a nucleophile attack it unless there's a rearrangement possible. In this case here, this is resonance delocalization, right? So that makes this carbon cation possible to be formed. All right, let's move to the second question here. What type of alkyl halide is this?
Secondary.
Yep, it's a secondary alkyl halide. Okay. What type of solvent do I have?
Strong.
Solvent?
Oh, aprotic.
This is
Phosphoric.
Protic. Oh my gosh. Okay.
It's all right. And what type of nucleophile do I have? I think you said it earlier.
Strong.
Strong.
Very good. So my conditions are going to favor which mechanism type?
SN1.
Yep, SN1. If you need to, the solvent usually always tells you that. So I need to prepare myself to look for what?
Rearrangement.
Yeah, potential carbon cation rearrangements. All right, I didn't do myself too big of a favor on this one, but we'll talk about the answer I wanted. There's two potential answers here, but I really wanted only one. All right, so I'm going to do this. I'm going to generate this carbon cation. Let's make this a little bit smaller. Okay. What can happen with this carbon cation?
Ring strain.
Yeah, ring strain. Now this is where it gets a little tricky. There is a hydride here that could shift, right? But the four-member ring is super strained. Okay, you guys know that, right? There's probably a lot of eclipsing bonds. Just has nothing going for it. So that ring is going to prefer to pop open. Right? Oh, I've been drawing my own arrows. Let me draw my own arrows. So I'm going to have this ring open. Why is it doing that? Okay. So all I'm doing is having one of these bonds to the ring neighboring this carbon cation. So this bond right here is going to pop open, all right, to extend itself out. All right, in doing so, I'm going to generate this right here. All right. And this is going to look like a ring. Get plus on that carbon. There. All right, let's see if I can get some numbers here for you guys. Keep track of things. Okay. Because the bond broke between 2 and 5, 2 and 5 and 1. Well, 2 used to have a bond to 3, 1, and 5, and there was an H there. But now only has one H and a bond only to 3 and 1. No bond to 5. That's why it gained a plus charge. Carbon 1 used to only have bonds to 2 and this methyl group here, but now it has a bond to methyl group 2 and 5, so it does not have a plus charge anymore. Okay. Let's get the numbers moved over to the 5'3". Okay, and so this translated back to a 2D structure. You got that 5' ring. So now my nucleophile comes in and attack, and my final product is going to be what here? I'm going to have a wedge OH product and also a dash OH product. All right, any questions here? Any questions? Yes, no?
No.
Good. All right, let's move down to this. How many more we got? Oh, we're doing good then. We'll be finished. All right. Can you guys help me out? Which mechanism type here? What type of alkyl halide?
Primary.
Primary. What type of nucleophile? Strong or weak?
Strong.
Strong nucleophile. All right, what type of solvent? Polar protic or polar aprotic?
Polar protic.
Yeah, that's right, polar protic. So what conditions are I probably asking for here?
SN1.
SC1.
SN1, that's right. You guys got that. Y'all almost ready to go. Starting to feel good. SN1.
No.
Why you said no?
I feel like it makes more
Because Dr. Cooper, what you do is you give us these problems that you work out with us with on the test. It be these problems times 20.
Thank you.
Oh,
Agreed.
It's like we'll get the basics. Like you give us the basic examples and we'll get them and we'll practice and we do fine. But on the test, it'll have 2-3 different bromines. It'll have 12 double bonds, and we don't know where to begin.
oh, this use the rules that you have. You know, when I make a test, I try to pray. I really do. I said, Lord, like, give me the questions that are fitting for the students, and that's what kind
Jesus did not give you them questions. Do not say
Sure
that.
he did not.
Every test I start off with is a blank sheet of paper. And I said, all right, I need to make a test. I need
And
some.
then you just start drawing stuff.
A vision comes to my mind, and I just go with it. I really attribute that to God. So those are the questions that the Lord wants you guys to have. You can handle
Well,
it.
he sent us the answers.
He can. He's working with you guys. Good. All right, help me out. This is SN1. What did I have to think about in the back of my mind?
Rearrangement.
Yeah, the rearrangement. So let's go ahead and draw out the carbon cation here. I'm gonna draw my line here. Okay. Okay. I got my carbon cation. Help me out. Is this stable?
No.
All right. Is there anything productive that can happen?
We could do a hydride or we could do a resonance.
Okay. Be careful. I don't see the hydride. Is there a potential hydride that can shift? So if I look at the neighboring carbon right here, there is a hydrogen here. Can that one participate in the hydride shift?
Yes.
No, it can't because it's attached to a carbon and a double bond. So the
Hydride shift is only for alkanes.
Yeah, only for alkanes, only for single carbons involved in single bonds. The strength of that hydrogen is super strong. It's an alkene, like so that bond is too strong. It's too hard to break. You can't break the H here. It won't shift. So in this case, I can't do a hydride shift. So what could I do?
Resonance.
Resonance. And I go for something that's primary to what if I do resonance here?
Tertiary.
One more time. Is it tertiary? Just take a look at that. I don't think it's going to be tertiary, but let's take a look.
Secondary?
Yeah. Maybe secondary. That's right.
Is it?
Let's take a look. So I'm going to get my resonance arrows here. I'm going to take this double bond. Yeah, I don't like the room. I didn't create enough room here.
Is it secondary?
Yep. Secondary is what we going to form.
Okay.
Sorry. Give me one sec. This is me just being a little picky. All right, this is going to move to be a secondary. Carbon cation. Good. So what happens now? Now I draw my product out, right? What's my product going to look like? I'm going to have a OME group here. All right, do I need to show stereochemistry here?
Yeah.
Yep, very good, I do. So that means that not only do I get this product,
Question, Dr. Cooper.
Yes, ma'am.
Are we sure it's stereochemistry because the carbon is chiral?
That's correct. That's exactly correct. All right, so I'm going to get these two products from this reaction in equal amounts. They'll be racemic. Okay, any questions so far on that question? Yes, no, no, yes?
One more time. So you for the where you put MEO, you got that from the nucleophile or the solvent?
In this case, it is the nucleophile. Yep. I mean,
Okay.
this nucleophile is strong. It will react with a solvent. So I guess what's another way to really try to strong nucleophiles react with the alkyl halide and the solvent. I can't say all that yet because we haven't talked about this being a base, but this is actually a base as well. So protic solvents are acidic, and this is going to also interact. But when this base interacts with this, it makes the same thing, right? Lithium hydroxide, the O is just going to grab an H, and you get OMe minus, and lithium is going to be attracted to it. So it just generates its own self in solution. But in this case here, the nucleophile is only the OMe. So even if you use methanol as the nucleophile, you still will have to lose the H, right? And this will take the H off. So it's the same thing. Does that help?
Yes, sir.
Okay, great. All right, let's move on to this next one here. Sorry, I forgot to do something on top here. What type of alkyl halide is this?
Secondary.
Yeah, secondary. What type of solvent do I have?
Polyprotic.
Yeah, polyprotic, and my solvent is also my wet. It's not gonna let me do anything.
Nucleophile.
Yeah, so this is known as what type of reaction here?
Savolysis.
Yeah, this is a savolysis reaction. Very good. So savolysis and all of this jazz is going to favor the SN1 mechanism type. So I need to prepare myself to investigate the what intermediate here. The carbon cation intermediate, right? Okay. So I'm going to form this carbon cation, right? All right. Is there anything that could happen productively here? Is there a hydride, methyl shift, ring expansion, resonance?
Resonance.
Okay. So take a look at this. There is a hydride right here, right? This is the carbon that has a plus charge. There's a hydride next door, two of them here, right? This could hydride shift, but if I did a hydride shift, I would generate a plus on that carbon. So I'll go from something that's secondary to something that's also what? Secondary.
Secondary.
So hydride is no good. But look at the carbon that has a plus over here or over there. There's no methyl group, so I can't do a methyl shift. Right over here, there's not really a ring. There's a ring one carbon away, but not right here. So there's no ring nearby neither, so I can't do a ring shift. But there is a pi bond, so I could do a resonance. So let's go ahead and do the resonance here. Sorry, these
JD running hot, ain't it?
Yes.
All I hear is your lips scratching on your paper.
I'm finally using a pencil.
Hallelujah.
Okay. So I'm going to get this resonance delocalization. And I'm going to generate, what type of carbon can I? Can you guys tell me?
Tertiary.
Yeah, very good. Man, it's not really what I wanted at, but I got no choice. Double bond there. And my plus charge is there. All right, so now what's going to happen?
I'll put the O ethanol on the third, on that, wherever the plus charge is.
Yeah, that's exactly right. So my final product is going to be now I'm going to have O F oxide here, right? It's an epoxy group here. Put that there. O. Do I have to show stereochemistry here?
Yes.
Okay, in this case I don't. Let's take a look and see why. So this carbon, and
No.
that's 3 carbons, and I do this side, that carbon, and that. So these 2 carbons are identical. So because there's 2 of the same groups, this center is not chiral. So a straight line is perfectly fine here. Okay, good. Boy, I'm having issues with this computer. Come on. It's got 2 more things. I think I was putting the answer in red. I can't remember. Okay, let's go down here. What type of alkyl halide is this down here?
Primary.
Yeah, this is primary. Type of nucleophile, strong or weak?
Strong.
Yep, strong. What type of solvent? Polar protic or polar aprotic?
Protic. Aprotic.
Yep, this is polar aprotic down here. Very good. So my reaction conditions are favoring which mechanism?
SN2.
Yeah, it's been a long time since we did SN2.
Sir, SN2.
Yes.
I think this is purple. Okay, let's go with an SN2. All right, so what's my product going to be?
Gonna be the pentagon, but it's gonna have
And A group.
the 3 lines attached to the end of it.
Okay, good.
And you hold on. We can't do stereochemistry for this one.
Yep, there's 2 hydrogens here, so there's no stereochemistry. That's right.
Can we get ones like this on the test?
Maybe. I haven't made it yet. I don't know. I'm pretty sure there has to be something like this on there. I'm still thinking about how to make the next test. But good. I don't have to show the mechanism here, do I? You know what? Let's just do it anyway. Anyone to say they didn't see the mechanism, didn't know how it's supposed to go. I don't think my computer can handle it anymore. Let's do this shit.
And can you also explain how it's not chiral? Because I kind of lost like what carbon I'm supposed to be looking at.
Well, it's the carbon that has a leaving group, and that carbon starts off with 2 hydrogens, and it still has 2 hydrogens in the bottom. So, because there's 2 of the same groups, it's not chiral. Okay. So the nucleophile attacked the carbon. I didn't realize that all of that got changed. All right. Leaving group left, and if you want to see one of the byproducts is sodium bromide. But again, I don't need to see that because it doesn't contain any carbons. All right, what type of alkyl halide is this last problem here? Are you guys still with me, the teams?
Secondary.
One more time.
Primary.
One more time.
Primary.
One more time.
Oh, benzylic.
All right, this last one is a tertiary benzylic alkyl halide.
Why is it benzylic? Is it because of the phenol group?
Yep, next to a phenyl ring. That's right. Okay, what type of nucleophile is this?
Strong.
That's right, it's strong. And what type of solvent is this?
Aprotic.
Polar, what was that?
Aprotic.
Yeah, polar aprotic. Okay, so what's the mechanism type here?
SN2.
SN2, that's right. So what's the product? How's the product look like for this one? Anybody? I got Ms. Durr, Ms. Moore, Ms. Holloway, Augustine, and Faber.
That's cool. We can't think that fast. But I got the same thing on the left, but I changed my wedge to a dash, and then I put another dash and put like a V on the end. What?
You said there's no reaction.
This
What?
was no reaction. You can never, you can never do an SN2 at a tertiary alkyl halide.
Oh, okay.
Keep that in mind. If you
Say that one more time.
Yep, no SN2 at a tertiary alkyl halide, right? Can you guys tell me why?
No SN2 at a tertiary. It's because it only has, well,
It's part of the rules you gave us.
Yep, it's part of the rules. The answer I'm looking for is the fact that the nucleophile can approach. It's too sterically encumbered, right? The tertiary, there's like 3 carbons. It has to come in from the back, right? It's seeing all this stuff. I'm not too sure if you guys remember the diagram that we talked about you can't see the black carbon from the tertiary alkyl ion. So the nucleophile can't approach. Especially not this one, not this isopropyl lithium. It's already got these two methyl groups that's blocking it too. So it's not even a straight line, it's kind of branched. There's no way that can come in here. Right? Yep, somebody has a question. Go ahead.
Yeah. Is it possible for there to be a reaction with, sorry, if there was like an alkene group, like a double bond, and we like resin, can we have a reaction?
If it's a double bond where on the substrate, on the chloride, this part here.
Yes, that part right there.
Yeah, you couldn't. No, you can't. You couldn't even substitute there. Not with the lithium version.
Not with the what?
No, that would be a vinyl chloride. So there's a double bond here with a chloride here. That would be a vinyl chloride. Vinyl chlorides don't do any substitutions. They don't do SN1 nor SN2.
So the reactions we are doing in our exam are substitution.
It's very low. I'm so sorry, favor is very low.
I don't know what's going on my computer. Okay, so I was asking, like on the exam, would the reactions we have be primarily substitution reaction?
Yeah, it's gonna be substitution and eliminations. Those are the two main reactions coming up in your test.
You don't really know elimination though.
No, we haven't done eliminations. We start those on Monday.
Thank you.
They're the opposite side of the same coin. Yeah, I decided to keep going for it. If you can do a substitution, you can do its brother, which is the elimination, or the sister. How do you feel about it?
I have a question actually.
Go ahead.
So with these like SN1 and SN2 reactions, okay, like the SN2 reactions, we primarily just like put nucleophile on the starting product, right?
Yes, you just substitute the Lehman group for the nucleophile. That's correct.
Okay. But for the SN1s, we like draw the intermediary product.
Yes. So I think I understand your question a little bit. So actually, everything in gray I don't need to see. That's all mental. But if you need to, you want to practice doing it on a sheet of paper, right? So only show this if I ask for the mechanism. But if I ask for the product, I'm just looking for this. I don't really necessarily need to see that, but it's good practice to do that, right? It's almost like, math. They might ask you to show you the work or just give me the answer. So typically I ask in a different set of questions to show me the work. And this is where you would do all those hydride shifts, methyl shifts, ring expansions, or resonance delocalization steps. So I hope that answers your question.
Yeah, another question.
Okay, go ahead.
Dr. Cooper, can you scroll up?
Yes.
So yeah, this one with the lithium hydroxide as the file.
This
that
one?
has like a bromine group.
Okay, this one.
Yes. So like why do we have like both these dash and wedge?
Oh yeah, because this carbon right here is chiral.
Mm-hmm.
So over here, this carbon has two H's. Over here, this carbon has one H in the methyl, and then it's another H. So this carbon is attached to 4 different groups. So you have to show a stereochemistry there. Did I answer your question?
Yes, you did.
Okay. Any other potential questions? Ask away.
So I'm trying to understand like the nature of the questions you may ask. When you say draw the major product, so is this still include like we still have to identify if it's SN1 or SN2?
Yep.
Or,
All that would be mental work. So when I ask for the major product, you would have to do all that work yourself. What I try to do so that the question doesn't hurt you point wise is that sometimes I set up where I ask you to tell me all this information, then give me the product so I can give you some partial credit. Right?
okay.
Dr. Cooper, I need to tell you, like, one of my concerns is, I know for me, time is a very big thing because me, I'm a, even though you say, do a mental, I draw everything out. And so with me, I could do these 10 problems, but it may take me 20, 30 minutes just to sit here and go through them. And so I know last time I was running out of time during my test because we had several of them. So can you give me a guess of how many of these are you gonna put on or like have to work out? Because I
Yeah.
know like even for our final exam, it's gonna be online and we're only gonna be given an hour for it. And I know an hour is not gonna be enough time for me.
Oh, I was gonna give you guys a little bit longer for the final exam. It's a little bit different format. Um, yeah, it's tricky. It's tricky. Trust me. As a faculty, and we talked about this even as a group. The issue that we have, the biggest concern with the way classes are being taught now is the level of cheating. Right? It's just the longer I spend time and I can't really see all students, the more people cheat. And I really feel like my position, I have to be a gatekeeper. There are some people that are really working hard. Typically, people that are here tonight, you guys are part of that group that really work hard for grades. But there's some people that look for any way they can to try to earn points that they don't deserve. So the extended time allows them to be able to work or to take advantage of that. So I'm very conscious of that. I am conscious of that. So the exam has to change. So I'm not going to put as many problems as I used to have, but or I have to ask those questions a little bit differently. So I do consider that. I'm hoping that the test that comes out will allow you enough time. But the best way to alleviate that, and I know everyone's not able to, if you don't feel like you have enough time, if you come in person, I can extend the time. I can give you 15, 20 minutes extra because I can look at you taking the test. But I know that that doesn't feel fair for people who aren't able to come and take it in person. So I can't really say that openly.
Yes. And and are you gonna be in your office today tomorrow for office hours? Because I wanted to see
For the test,
when were you gonna have our exam two graded?
yeah, you guys, yeah, I'm finishing those up now. I'm hoping I could be done with it tomorrow. Before class. If I'm not done with it before class, I'll be done with them after class. But you're more than welcome to come by. The paper versions are pretty much done. You guys can come look at them. The issue really is the online stuff. It's just kind of, I get things in different formats, and so I have to really kind of strain my eyes to see stuff. But if you want to come look at them, come by office hours. That's fine. Shoot me
Okay.
an email. Just the only thing now with office hours, we're just trying to shoot an email so that I don't get like a pile of students in my office because the department's they're already telling me watch out with that.
Uh,
They're concerned that I already had content one time. If I get contact again, they're not gonna be happy. So if you can shoot me an email, I can work with you there. But please feel free to come by.
Okay.
Dr.
And my extra credit didn't get put in. I sent you my
No,
screenshot.
I haven't put any extra credit in. I'm gonna do that when I put exam two grades in. Sorry.
Okay.
Yeah,
Okay.
yeah. I try not to do that because I get emails every day. You won't imagine. I get it. I probably got 4 emails this weekend. Oh, I was at this place. I was in it. I was there. So I don't get all the extra credits at one time. They like come within a whole week. So it's just to save myself that stress of like constantly updating that thing. I just wait until I get to, and then I tell you, well, I already put exam two in. It's kind of too late now for me to put extra credit in.
I have a question.
Yeah, go ahead.
For the radical test, the quiz you finished grading it because for mine it says some questions not yet graded still.
No, I haven't finished it for everyone.
Okay.
So what happens in the class, I wish it had happened this way. Everyone seems to finish the exam at the last possible minute. So it doesn't give me a lot of time to try to do it. But I did grade those that like had it done. I looked at it like 9 o'clock, maybe on Monday. There was a couple of people that had it finished and I could start grading then. But then I got like a whole stack of quizzes at the last minute. So there's nothing I can do then. So I'm looking at those now. Those are really on my to finish list now. So you'll see the comments. I just got a couple people saying they can't see comments yet. But within the next hour or two, you should see those grades in for those quizzes. That's easy to grade. Just one.
And this is the last question. I promise, Dr. Cooper.
That's
But
all.
are we gonna get like a curve? Is this class a curve class?
I usually curve at the exams. So I already curve exam 1. There'll probably be another. There's going to be an earn curve for exams, most likely for 1 and 2. So I think somebody asked me that on Friday. I just haven't set it up yet in Pearson, but there will be one assignment that will be used for a curve for your exam.
And so it won't hurt us if we take it.
No, it won't hurt you. No, that's right. Curves won't hurt. It won't. Yeah, your grade can't go down. It just added to your exam points. So they say that the curve is worth 15 points. If you get those 15 points, it adds to your exam points, right? So you can split it. It'll be split over your first 2 tests. So that's kind of how it works. If you don't score any points, your exam score stays the same.
Dr. Cooper.
Yep.
So I was doing the post test, post lecture on Pearson.
Yep.
And my main problem was like doing the mechanisms. Like I had them like written down in my notes. But like filling it in on Pearson is like way more complicated than I thought.
Yeah. There's it's very tedious. You want to keep training yourself because I'm pretty sure I have to use Pearson to do that extra credit. There's no way I can grade another exam in time. If you want to stop by during office hours, if we can do a virtual office hours, I could try to help you. It's a weird system. I don't like it personally. I don't like Pearson system. I'm actually trying to get my own app made. I'm just kind of like maybe a year or 2 out. But yeah, it's weird, but I can try to help you the best with that.
Thank you, Dr. Cooper.
Yeah, no problem.
Dr. Cooper, 2 more things. Okay, so you remember